Hello, how's everyone doing? There's no one even watching. Let me just change to full screen. So I got this, my website. Okay, so last stream I learned about power series and I learned about Taylor series. I still need to revise it a bit more. I'll be learning more about it off stream, and I think I might do another stream about chapter 5 and chapter 6 because I need to get my understanding right. This stream, I'll start with the parametric equations on polar coordinates. So introduction, let's just go straight to next. Also, I was watching videos about Taylor series. Uh, it's way more important than I initially thought. Just in case if I do exercises, I'll just keep the answer key open. Hmm. Consider the orbit of Earth around the Sun. Our year lasts approximately 365.25 days. But for this discussion, we will use 365 days. On January 1st of each year, the physical location of Earth with respect to the Sun is nearly the same, except for leap years, when the lag introduced by the extra one-fourth day of orbiting time is built into the calendar. We call January 1 day 1 of the year. Then, for example, day 31 is January 31st, day 59 is February 28th, and so on. The number of the day in a year can be considered a variable that determines Earth's position in its orbit. As Earth revolves around the Sun, its physical location changes relative to the Sun. After one full year, we are back where we started, and a new year begins. According to Kepler's laws of planetary motion, the shape of the orbit is elliptical, with the Sun at one focus of the ellipse. Yeah, with the Sun at one focus of the ellipse. We will study this idea in more detail in conic sections. Okay. Figure 7.2 depicts Earth's orbit around the Sun during 1 year. The point labeled F2 is one of the foci of the ellipse. The other foci is occupied by the Sun. If we superimpose coordinate axes over this graph, then we can assign ordered pairs to each point on the ellipse. Then each x value on the graph is a value of the position as a function of time, and each y value is also a value of position as a function of time. Therefore, each point on the graph corresponds to a value of Earth's position as a function of time. Okay, so far so good. We can determine the functions for xt and yt, thereby parameterizing the orbit of the Earth around the Sun. The variable t is called an independent parameter and in this context represent time relative to the beginning of each year. A curve in the xy plane can be represented parametrically. The equations that are used to define the curve are called parametric equations. If x and y are continuous functions on t on an interval I, then the equations xt and yt are called parametric equations, and t is a parameter. The set of points xy obtained as t varies over the interval I is called the graph of the parametric equations. The graph of parametric equations is called a parametric curve or a plane curve and is denoted by C. It was denoted by C. If we had a 3D graph, would there be a separate variable of t? Like if you have a 3D graph with a separate variable of t, would be like able to see all the slices all the way the xy graph can be with varying t values. Graphing a parametrically defined curve. Sketch the curves described by the following parametric equations. To create a graph of this curve, first set up a table of values. Since the independent variable in both xt and yt is t, let t appear in the first column, then xt and yt will appear in the second and third columns of the table. So this is what the graph looks like. The arrows on the graph indicate the orientation of the graph, that is the direction that a point moves on the graph as t varies from -3 to 2. Yeah, then let me just test this. Y is equal to 2t plus 4. Is there a way I can write parametric equations on Desmos? Can I no why how do I combine these two? T minus 1 to t plus 4. It goes from -3 to 2. Okay, t square minus 3 and then 2t plus 1. Graph looks like this. 4 cos t and 4 sin t. Oh, that makes sense. T can be the angle. Eliminating the parameter. To better understand the graph of the curve represented parametrically, it is useful to rewrite the two equations as a single equation resulting in the variables x and y. Then we can apply any previous knowledge of equations of curves in the plane to identify the curve. For example, the equations describing the plane curve in 7.1b are these three. And let me just write it down. Let's see. So x is t square minus 3. Voila. I'm feeling cold, so I'm writing slower. Y is 2t plus 1. Y is equal to 2t plus 1. So what we can do is, we can write this as x plus 3 square root equals t, and then y is plus 1. Whoops. X. Let's see what we get. Y is equal to root x plus 3 plus minus. How do I do plus minus? X plus 3. 2 times x plus 3. And t is from minus 2 to 3. So then t square would be 4 to 9, right? And if you subtract 3 from both sides, you get 1 to 6. They're defining it in terms of x. Six, 7, and 1, 5. What do we have here? 6, 7. It says 1, negative 3. There's negative 3 here. Wait, so the range would be minus 4 to 3 times 4, 3 times 2 is 6. Minus 4 to 6. Be plus 1. In minus 3 to 7. Y would be from minus 3 to 7. So it's only defined at minus 3 at the bottom. Eliminate the parameter for each of the plane curves described by the following parametric equation and describe the resulting graph. So we have root 2 x is equal to root uh, plus 4, y is equal to 2t plus 1, and t is minus 2 to 6. So x squared minus 4 2 is equal to t, y is equal to the 2 and 2 cancel, x squared minus 4, x squared minus 3. And if this is the range for t, then we have minus 4 t 12. It's plus 1, right? So minus 3 to 13. And 16 and the root of it. So these are the values x and y can take. Y is x squared minus 3. X squared minus 3, 0 and 4. Y is minus 3 to 13. Okay. This is the graph I got. What about the next one? We are left with 3 sine arc cosine x over 4. We need a calculator for this. Cos square plus sine square is 1. They use this formula. And then they got this. So far, we have seen the method of eliminating the parameter, assuming we know a set of parametric equations that describe a plane curve. What if we would like to start with the equation of the curve and determine a pair of parametric equations for that curve? This is certainly possible, and in fact, it is possible to do so in many different ways for a given curve. This process is known as parameterizing of a curve, parameterization of a curve. Find two different pairs of parametric equations To represent the graph, y is equal to x square minus 3. We have y is equal to 2x square minus 3. So we can write this and then this. Uh, like that. That's one way. Or they just did it like this. They just replaced x with t. I guess that's one way of doing it. Cycloids and other parametric curves. Imagine going through a bicycle ride through the country. The tires stay in contact with the road and rotate in a predictable pattern. Now suppose a very determined and is tired after a very long day and wants to get home. So he hangs on to the side of the tire and gets a free ride. The path that this ant travels down a straight road is called a cycloid. Okay, right. A cycloid generated by a bicycle or a bicycle wheel of radius a is given by the parametric equations. Xt is equal to a t minus sine t, and y is equal to a 1 minus cos t. To see why this is true, consider the path that the center of the wheel takes. The center moves along the x-axis at a constant height equal to the radius of the wheel. So a is the height of the wheel. Sorry, a is the radius of the wheel. Yeah, so the x value would be a times sine t, but the x value is shifted. Hold on. No, not like this. I think it's better if I define y. Y is equal to why is it 1 minus cos t? The radius is a. The coordinates of the center can be given by the equations a, t, and a. For any value of t. This is the coordinates of the center of the wheel. I don't understand where the 1 minus cos t come from. How do I make a parametric equation in Desmos? Hold on. Let me see. Like, I don't understand how they're leaving a line behind. Parametric curves. Okay, wait, hold on. Let me see how they do this. I don't know how they do it. Oh, just write it like that. T is negative 3, 2. Anyways, x is a sine t, then y is a cos t. Let's try 10. What if we have minus? Oh, I see. This minus 1. Minus. Hey, let me think. Viscosity starts at 1 and keeps decreasing, right? So if we do minus, we'll have the reverse effect. And of course, we do plus A so that it reaches the end. So it touches 0. Cos starts with 1, so the height is A. Anyways, a possible parameterization of a circular motion of the ant relative to the center of the wheel is given by x is equal to minus a sine t and then y is equal to minus a cos t. The negative sign is needed to reverse the orientation of the curve. Sine t minus t. T is like how much the graph is being shifted by. Now suppose that the bicycle wheel doesn't travel along a straight road but instead moves along the inside of a larger wheel. The green circle is traveling around the blue circle in a counterclockwise direction. The green circle is traveling around the blue circle in a counterclockwise direction. A point on the edge of the green circle traces out the red graph, which is called a hypocycloid. Okay, so the cycle is going around inside a circle. So this is the wheel, and the point it traces is this diamond shape. The general parametric equation for a hypocycloid are xt a minus p cos t plus p cos a b over bt. These equations are a bit more complicated, but the derivation is somewhat similar to the equations of these for the cycloid. In this case, we assume the radius of the larger circle is a and the radius of the smaller circle is p. Then the center of the wheel travels along a circle of radius a minus p. This fact explains the first term in each equation above. The period of the second trigonometric function in both x and y is equal to 2 pi b over a minus b. The ratio a over b is related to the number of cusps on the graph. Cusps are corners or pointed ends of the graph, as illustrated in figure 7.11. This ratio can lead to some very interesting graphs depending on whether or not the ratio is rational. Figure 7.10 correspond to A is equal to 4 and B is equal to 1. This results in a hypocycloid with 4 cusps. Hypocycloids have an infinite number of cusps, so they never return to this in these cases. Wait, hold on. The last two hypocycloids have irrational values for A over B. In these cases, the hypocycloids have an infinite number of cusps, so they never return to their starting point. These are examples of what are known as space-filling curves. Okay. Is there any more? No, it's about exercises. We assume the radius of the largest circle is A and the radius of the smallest circle is B. Yeah, I think I sort of understand it. Should I do some exercises? What are they about mainly? Do a curve into rectangular form. No sketch is necessary. Okay, let's just go to the next chapter. I need to read more about the last part. About the circles. Calculus of parametric curves. We start by asking how to calculate the slope of a line. Wait, should I read the introduction? Nah, never mind. Consider the plane curve defined by the parametric equations x is equal to 2t plus 3 and y is equal to 3t minus 4. T goes from minus 2 to 3. The graph of this curve appears in 7.16. It is a line segment starting at minus 1, minus 10 and ending at 9, 5. We can eliminate the parameter by first solving the equation x is equal to 2t plus 3 for t, and then we are left with this. Y is equal to 3x over 2 minus 17 over 2. Did I do this? No. Maybe I did and I just forgot. Isn't this the first one I did? Never mind. The slope of this line is given by 3 over 2. Next we calculate the derivative of x with respect to t and derivative of y with respect to t. This gives derivative of x is 2 and derivative of y is 3. Notice that dy over dx is equal to dy over dt divided by dx over dt, which is 3 over 2. This is no coincidence. Consider the plane curve defined by the parametric equations x is equal to xt and y is equal to yt. Suppose that derivative of x with respect to t and derivative of y with respect to t exist, assume that derivative of x is not 0, then the derivative dy over dx is given by this. This theorem can be proven using the chain rule. So if we use the chain rule, we get this. Y is equal to f of xt. Okay, I understood. Finding the derivative of a parametric curve. Calculate the derivative dy over dx for each of the following parametrically defined plane curves and locate any critical points on their respective graphs. Critical point as with respect to t. Where dy by dx is 0. So 7.4a. xt is t square minus 3. To t minus 1. And t is from minus 3 to 4. So this is 2t. This is 2. So 2 over 2t. Divided over t. So I don't think there's a critical point here. Critical point is when it's 0, right? This derivative is undefined when t is equal to 0. Calculating x0 and y0 gives x0 square minus 3 is equal to minus 3. Y0 is equal to minus 1. which corresponds to the point on the graph, which corresponds to the point minus 3 minus 1 on the graph. The graph of this curve is a parabola opening to the right, and the point minus 3 minus 1 is its vertex as shown. Find the equation of the tangent line to the curve defined by the equations. Okay. Now we did this, right? 2t from minus 3 when t is equal to 2. So what are we trying to find? The equation of the tangent line to the curve defined by the equation. When t is 2. So x of 2. What's this? Example 7.5. T is 2. Then x2 is 2 square minus 3, which is 1. 2 times 2 minus 1. Add 2. Add 2 is equal to 1 over t, which is 2. So the tangent line is y is equal to mx plus c. Y is equal to 3. 1 over 2 plus c. C is equal to 2.5. Y is equal to x over 2 plus, like that. Okay, second order derivatives. Our next goal is to see how to take second order derivative of a function defined parametrically. The second derivative of a function y is equal to f of x is defined to be the derivative of the first derivative. That is d square y over dx squared. We can replace y on both sides of this equation with dy over dx. This gives us, let's see, so we get d over dx times dy over dx, and then dy over dx, it stays here, but we are dividing both sides by dt. If we know dy over dx as a function of t, then this formula is straightforward to apply. So I take derivative of y with respect to x, and then you derivate it again with respect to t, and then you divide it by derivative of x with over, yeah, with respect to t. T square minus 3 and 2t minus 1 again. Seven 7.6. t square minus 3. And then t is from minus 3 to 4. Supposed to find the second derivative, we need dy over dx. Y is equal to 2 root d root x plus 3. This is 2t. This is just 2. So 1 over t. And then so derivative of this with respect to t, t to the power of minus 1. This becomes minus t square. And then this remains 2t. This is I'm guessing this is the answer. Yeah. Integrals involving parametric equations. Note that we have seen how to calculate the derivative of a plane curve. The next question is this: how do we find the area under a curve defined parametrically? Recall the cycloid defined by the equations xt is equal to t minus sine t and yt is equal to 1 minus cos t. Suppose we want to find the area under the shaded region in the following graph. To derive a formula for the area under the curve defined by the function, we assume xt is increasing on the interval t a b. xt and xt is differentiable. And start with an equal partition of the interval a t, which is between a and b. So suppose t naught is equal to a, which is less than t1, less than t2, all the way till tn, which is b. Consider the following graph. We use rectangles to approximate the area under the curve. The height of the ith rectangle is y is equal to ti minus 1. So an approximation to the area is let's see what they're doing here. So yt minus 1 xt minus xti minus xt minus 1. So this width times this height. So as this interval remains constant, right? This ti minus 1. So if you take this to 0, um, this would go to this by definition is the derivative of x with respect to t as the as this ti minus 1 goes to 0, and dt. Okay, I think I can understand. This follows from results obtained in calculus 1 for the function. Okay, the Riemann sum, the area is this yt and derivative of x with respect to t times dt. So this is the area under the curve. Okay, let's try. Xt is t minus sine t. And then yt is 1 minus cos t. So got this derivative of sine is cos. And then the integral. We need the indefinite integral, right? So no, area under this from 0 to 2 pi is cos t squared. So yt times this dt. Wait, if I expand this, I get 1 plus cos square t. This part looks familiar. Hold on, I can write the 1 plus, uh, hold on, sine square t is cos square t. So 1, break this to the other side. I can write it here. So this is equal to plus 1 minus sine square t. The 1 and 1 cancel out. Oh no, this is incorrect. I was thinking of something else. But I think I can use this as well. 1 minus cos 2j over 2. Integral derivative of sine is cos. So integral of cos is sine, right? I'll bring minus 2 outside. Derivative of sine 2t is cos 2t times 2. Derivative of sine 2t is cos 2t times 2. So then I can do this. Sine 2t over 2 minus t. And then I have to just substitute in the values. Sine 0 is 1, right? And then sine 2 pi is also 1. Yeah, it's the same. No, sine 0 is not 1, sine 0 is 0. So is sine 2 pi. So this gets removed over here as well. So we are just left with minus t. Minus 2 pi. Half minus 2 pi. Let's see. Why did they get 3 over 2? Okay, so this is correct. 1 plus cos 2t. Hold on a minute. I changed where did I make a mistake? Minus 2 sine t, nothing is going to happen because it's going to get cancelled out. You put 2 pi here, we are left with 3 pi because 2 and 2 cancel out. And let me see what's happening. How did they get over 4? Oh, because of this half. There's a mistake somewhere. Because I'm getting just pi. Cos 2t minus 1 over 2. This should be equal to sine square. Or minus sine square. Cos square. I have no clue where the mistake is. Is it this sine 2t? I think it's this. Sine 2t is sine 4 pi over 2 minus 2 pi, right? And sine 0 is 0 and then 0 here. So this part, that part doesn't matter. What is sine 4 pi? That's also 0. So we are left with just pi. It's 3t over here, but minus just minus t. Okay, if someone in the comments can tell me what the issue is, it would be appreciated. Arc length of a parametric curve. In addition to finding the area under a parametric curve, you sometimes need to find the arc length of a parametric curve. In the case of a line segment, arc length is the same as the distance between the endpoints. If a particle travels from point A to point B along a curve, then the distance that particle travels is the arc length. To develop a formula for the arc length, we start with an approximation by the line segments as shown in the following graph. Given a plane curve defined by the function xt and yt from a to b, we start by partitioning the interval ab into n equal subintervals. The width of each subinterval is given by b minus a over n. So it's equal in the x-axis, right? You can calculate the length of each line segment like this. D1 is from the Pythagorean theorem from this to this, from this line, and using the Pythagorean theorem we find the diagonal line. To add these up, we let S donate the arc length and we let S donate the exact arc length and Sn donate the approximation by n line segments. We assume that xt and yt are differentiable functions of t. Then the mean value theorem applies. So in each subinterval there exists t hat and wait. One is for x, one is for y. So t hat and then another t hat such that. Right. Okay, I see. So between xt minus xtk minus xtk minus 1. Okay, I understood. So what are they getting at? You end up with this. Then if we take this to infinity, we take the intervals to infinity, we end up with this. The two t's are both contained within the same ever-shrinking interval of width delta t, so they must converge to the same value. From t1 to t2, dx, derivative of x with respect to t, derivative of y with respect to t, dt. Finding the arc length of a parametric curve. And then derivative of cos is minus sine. Derivative of y with respect to t is cos from 0 to pi square square dt. So we have 9 sine square t, then 9 cos square t, and then we can extract 9 out. Yeah, left with plus minus 3. So 3 d by 0, which is, well, it's arc length, right? So it's now minus. Okay, this is the last thing. Now what's all this? surface area generated by a parametric curve. We call the problem of finding the surface area of a volume of revolution. We derived a formula for finding the surface area of a volume generated by a function y is equal to f of x from a to b, revolved around the x-axis. We now consider a volume of revolution generated by revolving a parametrically defined curve. X is equal to xt, y is equal to yt from a to b on the x-axis as shown in the following figure. The analogous formula for a parametrically defined curve is, right, it's this. Provided that yt is not negative in a to b. Finding the surface area of a sphere of radius r centered at the origin. Wait, we don't need parametric equation for this. Okay, let's go to the next chapter. I think let me just skim read this entire chapter. I just need to know the material. And then I might come back to it in later streams. So polar coordinates. To define the coordinates of a point in a polar coordinate system, consider 7.27. The point P has Cartesian coordinates x, y, and the line segment connecting the origin to the point P measures the distance from the origin to point to P and has length r. The angle between the positive x-axis and the line segment has measured theta. This observation suggests a natural correspondence between a polar coordinate xy and the values r and theta. This correspondence is the basis of a polar coordinate system. I see, so instead of defining it by xy, defining it by theta and r is the length of the line. And then in a three-dimensional graph, there'll be a second r for the other axis. Using right triangle trigonometry, the following equations are true for point P. Cos theta is x over r. So x is r cos theta, y is r sin theta. R square is x square plus y square, and tan theta is y over x. R is always positive, right? Then theta can vary from 0 to 2 pi. Each point xy in the Cartesian coordinate system can therefore be represented as an ordered pair. In the polar coordinate system, the first coordinate is called the radial coordinate and the second coordinate is called angular coordinate. Each point in the plane can be represented in this form. Note that the equation tan theta is equal to y over x has infinite number of solutions for any ordered pair xy. Yeah, what do you mean infinite solution? or in between, yeah. Oh, I see. However, if we restrict the solutions to values between 0 and 2 pi, we can assign a unique solution to the coordinate at which the original point xy is located. Then the corresponding value of r is positive. Converting between rectangular and polar coordinates. Convert each of the following points into polar coordinates. Let's try -3 and 4. 7.11 b. Sorry, I'm making a blanket over myself, so that's why I'm moving around a lot. Um, so -3 and 4. -3 and 4. So r is 5, and then tan theta is x over y, right? Sorry, it's y over x. Hold on, tan theta. Oh yeah, opposite over adjacent. So confused for a minute. So chi to guess 1.75. So theta is 0.92729. Let me see what is spot B. It says 2.21. R tan 4 over 3. Uh, Okay, yeah, I understand. Because in a circle, wait, tan is defined from here. So like pi to 0 to pi over 2, and then 0 to minus pi over 2. That's where arctan is defined. Arctan x. Yeah, yeah. So it's between minus pi over 2 and pi over 2. But the thing is, if it lies over here, then we need to add pi to get the value of pi over here, to get the value of theta over here. So that's why they're adding pi. 2.21. Let's try 5 root 3 minus 5. X is 5 root 3, y is minus 5. Twenty-five times 3 is 75. Plus it with 25. You get 100, so this is 10. Tan theta is opposite over adjacent. Theta is equal to arctan. We get this, and then we add by 2.61. 6 minus pi over 6. Why does it say minus pi over 6? Oh, yeah. Because it's in the fourth quadrant. It's in this quadrant. So that's why it says minus pi over 6. Right. Let's try one of this. 3 and pi over 3. 3 and pi over 3. This is E. Hmm. Okay, let's see. This is sine theta. Since it's r times, then it's r sine theta. 3 times sine pi over 3. Okay, let's see if I'm on the correct path. Yep. Now let's see what's next. The polar representation of a point is not unique. For example, polar coordinates 2 pi over 3 and 2 pi 7 pi over 3 both represent the point 1 root 3 in a rectangular system. Also, the value of r can be negative. Okay, this I didn't know. Therefore, the point with the polar coordinate minus 2 4 pi over 3 also represents the point 1 root 3. Okay. The line segment starting from the center of the graph going to the right is called the positive x-axis in the Cartesian system is the polar axis. The center point is the pole or origin of the coordinate system and corresponds to r is equal to 0. The innermost circle shown in figure 7.28 contains all points a distance of 1 units from the pole and is represented by the equation r is equal to 1. Okay. The line segments emanating from the pole correspond to fixed angles. To plot a point in a polar coordinate system, start with the angle. If the angle is positive, then measure the angle from the positive axis in a counterclockwise direction. If it is negative, then measure it clockwise. If the value of r is positive, move that distance along the terminal ray of the angle. If it is negative, move along the ray that is opposite the terminal ray of the given angle. Plotting points in the polar plane. Plot each of the following points on the polar plane. Okay. Polar curves. Now that we know how to plot points in the polar coordinate system, we can discuss how to plot curves. In the rectangular coordinate system, we can graph a function y is equal to f of x and create a curve in the Cartesian plane. In a similar fashion, we can graph a curve that is generated by a function r is equal to f theta. The general idea behind graphing a function in polar coordinates is the same as graphing a function in rectangular coordinates. Start with a list of values for the independent variable theta in this case and calculate the corresponding values of the dependent variable r. The process generates a list of ordered pairs which can be plotted in the polar coordinate system. Finally, connect the points and take advantage of any patterns that may appear. The function may be periodic, for example, which indicates that only a limited number of values for the independent variables are needed. Plotting a curve. Create a table with two columns. The first column is for theta, the second column is for r. Create a list of values for theta. Calculate the corresponding r values for each theta. Plot each ordered pair. Connect the points and look for a pattern. Okay, let's see for sine theta. Can I change this to polar? Minor grids, yeah. And then I can do for sine x for sine theta. Is there no theta? No. Hold on. R is the radius, right? Shouldn't this be a Y? I'm getting confused. R is sine is 0. So R is 0. Sine is pi over 3. Then yeah, I think I understood. Transforming polar equations to rectangular coordinates. Rewrite each of the following equations in rectangular coordinates and identify the graph. Pi is equal to theta is equal to pi over 3. Where is R? Uh, Wouldn't R is equal to 3 just be a circle of radius 3? Because it's defined for all theta. And theta is equal to pi over 3 is just a straight line, right? So 7.13 pi over 3 R sine pi over 3 cos pi over 3 R is equal to x over sine pi over 3. Um, then I get tan, because sine divided by cos is tan, then cos divided by sine is, let's see, y equals x over tan pi over 3. Is this correct? Tan is sine over cos, right? I think I mixed these two up. Yeah. 9 makes sense. Now we do r is equal to 3. 3 cos theta 3 sine theta 9 cos square theta plus it with 9 sine square theta to 9, which is equal to r square. Yeah, so if I do then I get r is equal to 3. R is equal to 6 cos theta minus 8 sine theta. Mm, cos theta sine theta minus 8 sine square theta. So then x minus 6 cos square theta over negative 8 is equal to y plus 8 sine over 6 8 times 8 is 64. I don't even know if this is correct. R square is equal to s square plus y square. How did you get this? R square is equal to 6r square minus 8 r sine theta and 6x minus 8y. We have now seen several examples of curves defined by polar equations. A summary of some common curves is given in the table below. K spiral is equal to b theta. Cardioid. This is a cardioid. Any of these equations. A lemma rose. Cardioid is a special case of lemma. I don't even know if this is how you pronounce it correctly. Limaçon, in which a is equal to b and a is equal to minus b. The rose is a very interesting curve. Note that the graph r is equal to 3 sine 2 theta has 4 petals. However, r is equal to 3 sine 3 theta has 3 petals as shown. Because if the coefficient of theta is even, the graph has twice as many petals as the coefficient. The coefficient of theta is odd, then the number of petals equals the coefficient. Symmetry in polar coordinates. When studying symmetry of functions in rectangular coordinates in the form y is equal to f of x, we talk about symmetry with respect to y-axis and symmetry with respect to the origin. In particular, f of negative x is equal to f of x for all x in the domain of f, then f is an even function. Its graph is symmetric with respect to the y-axis. If y is equal to negative x, which is equal to negative f of x for all x in the domain of f, then f is an odd function and its graph is symmetric with respect to the origin. Symmetry in polar curves and equations. Consider a curve generated by a function r is equal to f theta in polar coordinates. The curve is symmetric about the polar axis if for every point r theta on the graph, the point r minus theta is also on the graph. Similarly, the equation r is equal to f theta is unchanged by replacing theta with minus theta. The curve is symmetric about the pole. So first symmetry is about the polar axis. So this, where the theta is the same as f of theta is the same as f of minus theta. Second is about the pole. If for every point r theta on the graph, the point r pi plus theta is also on the graph. Similarly, the equation r is equal to f theta is unchanged when replacing r with minus r or theta with pi plus theta. Okay, so if it's defined here, it's defined, let's say here, and it's also defined pi plus theta, then it's symmetry around the pole. If this is true for all theta, the circle is symmetric both ways, right? The curve is symmetric about the vertical line. Theta is equal to pi over 2. If for every point pi r and theta on the graph, the point r and pi minus theta is also on the graph. Similarly, the equation r is equal to f theta is unchanged when theta is replaced by pi minus theta. So this one is symmetric about the polar axis. This is symmetric around the pole. This is symmetric around the vertical with respect to the vertical. Okay, how much is left? I think I will just finish these two and then go to sleep, I guess. Areas of region bounded by polar curves. Consider a curve defined by the function r is equal to f theta, where theta is between alpha and beta. So here to here. Our first step is to partition the interval into n equal subintervals. The width of each subinterval is given by the formula delta theta is equal to b minus alpha over n. And the ith partition point theta is given by the formula theta is equal to alpha plus I delta theta. Each partition defines a line with the slope tan theta passing through the pole as shown in the following graph. Oh, so they are making curves which is equidistant to the pole. The line segments are connected by arcs of constant radius. The formula for the area of the sector of a circle is illustrated in the following figure. Area is half theta r square. Uh, did I write the area, the circle here? No, I need to make sure. I need to remember to write it. Recall that the area is pi r squared. When measuring in radians, 360 degrees is equal to 2 pi radians. So instead of the whole area, we only want theta over 2 pi of it. You're left with half pi r squared, where theta is in half theta r squared, where theta is in radians. So a1 is this. We just substitute in the values, and then the sum of area is this. So the integral would be, alright, to read this. This gives the following theorem. Area of a region bounded by a polar curve. Suppose f is continuous and non-negative on the interval alpha, which is less than theta, which is less than beta. The area, yeah, well, what do they mean by this? B minus alpha is less than 2 pi. The area of the region bounded by the graph R is equal to f theta between the radial lines. Theta is equal to alpha and theta is equal to beta is this. Finding an area of a polar region. So we need to integrate it half r squared d theta. Find the area of one petal of the rose defined by the equation 3 sine 2 theta. Sine 2 theta. Let's see. So we are going from 0 to pi over 2, right? What number is this? 7.16. We have 3 sine 2 theta So 9 sine square 2 theta theta. Sine square 1 minus cos 2j over 2. So take half out, we are left with 9 over 4. Theta, I guess derivative of sine is cos. Derivative of sine 4 theta or 4 is cos 4 theta. This is correct. We will forget about the 0 case, pi over 2. So sine 4 times pi over 2 is sine 2 pi, which is 0. So 9 pi 4 times 2 is 8. Yes. Finding the area between two polar curves. R is equal to 2 plus 2 sine theta. R is equal to 6 sine theta. So find the area outside the cardioid and inside the circle. Find the area outside and inside the circle. So we take the area of the circle, then subtract it from the area. They intersect at pi over 6, right? Hold on. Wait a minute. So from pi over 6 to 5 pi over 6, I would get Hold on. How do I explain this? So I will get all of this area, right? With this. Let me just. So 5 pi over 6 and pi over 6. So basically I'm getting this area. So if I take all of this, subtract this area, I'm still left with this. No, actually I should take this, find the area. I was thinking about finding the area of the whole circle, but I think I have to find the area from this point onwards. This, all of this. I take the green part and subtract the red part. Yeah. So they intersect at sine pi over 2. I mean sine, they intersect at theta is equal to pi over 6. So basically, I won't solve the entire thing, but I'll tell you what I'm trying to do. 7.17. Integral. So first of all, we need to know the intersection. So 2 sine theta is equal to 6 sine theta. And this leaves us with 4 sine theta Mm, let's see, sine pi over 6 is half. Yeah, so this exactly is the intersection point. And now we take sine theta squared d theta minus it with That's the general idea. And let's see if they're doing the same. Oh yeah, I forgot the half. Half. And then the final value is 4 pi. Arc length and polar curves. Okay, I think the proof I will study it in my study it off stream. What they get is, okay, wait, what? F theta, no, r squared plus derivative of r with respect to theta squared. Okay, so example 7.18. Where are we finding the arc length? Arc length. How are we doing this? Do we do 0 to 2 pi? What happens if we remove the plus 2? Wait, if we are calculating the area of this, if we do 0 to 2 pi, wouldn't this one overlap? Let's try pi. Okay, uh, over 3, or maybe it's 3 pi over 2. So we got this. So when is r equal to 0? Is that when theta is arc sine minus half, right? Which is what? Hold on. Sine minus half sine minus pi over 6. I want to get like the exact value. Can we get a fractional value? Yeah. 11 over 6. 11 pi over 6. Theta is equal to 11 pi over 6. Where is the line? How do I draw a straight line at 11 pi over 6? Let's say r is 1, then x is equal to this. It's already mentioned here. The thing is, I don't understand. Can I make it vary? Can't click on this, right? Can click on this. 3 pi 4 pi over 3. It's 4 pi over 3. It's going till here. Seven pi over 6. I think it does reach 0, but like when it comes back. So at 7 pi over 6, it reaches here. But from 7 pi over 6 onwards, how do we find the area? Because it like... Anyways, I got distracted. R squared derivative of sine theta is cos theta. So the length is equal to r squared plus d theta. For sine theta for sine square theta cos square theta is just equal to 4. 4 plus 4, 8. We can extract 4 out, right? Divide both sides by 4. 2. And then we get 2 here. You're finding the arc length, so this is going to be positive. And I'm stuck here. Oh, it's cos theta, not sine theta. How did it get 8? How did it get 8? Oh, 2 times. Yeah, yeah, yeah. But that's just R. Okay, we can use trigonometric rules, right? Let's see, product formula. Hold on. Four cos squared j is equal to 2 cos 2j plus 2. So I guess I can do this. 2 cos square theta over 2. This is actually 4. And then I guess we can take 2 out from here. We get 4. I mean, I already saw the answer, so. But I understood what they did. Okay, conic sections. I did some studying about conic sections. Algebra, geometry. And I wrote certain things about parabola and hyperbola. So I hope some things are familiar. Conic sections have been studied since the time of the ancient Greeks and were considered to be an important mathematical concept. As early as 320 BCE, such Greek mathematicians as, okay, Apollonius and Archimedes were fascinated by these curves. Apollonius wrote an entire 8-volume treatise on conic section in which he was, for example, derive a specific method for identifying a conic section through the use of geometry. Since then, important applications of conic sections have arisen. For example, in astronomy, the properties of conic sections are used in radio telescopes, satellite dish receivers, and even architecture. Conic sections get their name because they can be generated by intersecting a plane with a cone. A cone has two identical shaped parts called napes. I don't know how you pronounce it. One nape is what most people mean by cone, having the shape of a party hat. A right circular cone can be generated by revolving a line passing through the origin around the y-axis as shown. Conic sections are generated by the intersection of a plane with a cone. So yeah, the napes. Okay, so from what I understand, if it's like perpendicular to, if it's like parallel to the x-axis, then the intersection would be a circle. If the plane is like parallel to the side of the cone, then the shape you get is a parabola. If the plane is more steep than the parabola plane, then the intersection you get is a hyperbola. If the plane is less steep than the parabola plane, but not exactly parallel to the x-axis, then the intersection you get is an ellipse. So if it's flat, circle. If it has small slope, then the intersection is an ellipse. If the slope is parallel to the side of the cone, then the intersection you get is a parabola. The slope has, uh, if the slope is larger than this one, is called hyperbola. A parabola is a set of all points whose distance from a fixed point called the focus is equal to the distance from a fixed line called the directrix. The point halfway between the focus and the directrix is called the vertex of the parabola. Wait, hold on. In this part, I made the equivalence. I showed the equivalence of the standard form equation and the focus directrix definition. So the standard form parabola so the standard form is like a x squared plus bx plus c. This you will get a shape like this. This is a parabola, and then or another definition is that there is a focus and a directrix, and such that the distance between the focus and the directrix is equal. So the loci of all of these points will form a parabola. So you choose a focus, you choose a directrix, and the locus of those points, all the equidistant points, is called a parabola. Over here, I derived, I showed the equivalence of the definition. The point halfway between the focus. Okay. So, this bottom side over here This is the vertex of the parabola. So in this case, it would be here. So at x is equal to z, parabola has this vertex. So over here, yeah, what I derived was the standard formula. I think I will rewrite some of it. So over here, this is what I end up with. So I started with this, where x minus, so any point xy, and this here is zp. This is the point of the focus. So what I started with was that x minus z square plus y minus p square. Sorry, x minus z square plus it with y minus p square and then square root. It should be equal to d. Right? And then the second definition of d is y minus d. I don't know why this is the case. Oh, yeah. So this point is x and y. So you have y minus d will give you d. I was looking at this. I think I should erase this to remove confusion. Okay, so I start with this, expanded, and I simplified, and I was left with this, which can be written as a x square plus bx plus c. But I mean, they already did it here. Given a parabola opening upwards with a vertex located at hk, and focus located as hk plus p, where p is a constant, the equation for a parabola is given by this. This is the standard form of a parabola. Wait, I think I got this wrong. This is the standard form. This over here is the standard form. In addition, the equation of a parabola can be written in the general form. Though in this form the values of h, k, and p are not immediately recognizable, the general form of a parabola can be written as this. Okay, so what I derived over here is the general form. Put the equation x squared into the standard form and graph the resulting form parabola. So standard form is like this. $7.19. X squared minus 4x minus 8y plus 12. Y is equal to plus k. This is x squared minus 2xh So minus, so 4 is equal to 2h. Eight is, no, 12 is equal to, hold on. Four pk. Where is y? Yeah. And then 8 is equal to p 4p. K is equal to 1. So y is equal to 1 over 8 x minus 2 square plus 1. Yeah. An ellipse is a set of all points for which the sum of their distances from two fixed points, the foci, is constant. The points P and P and P naught are located at the ends of the major axis of the ellipse have coordinates a0 and minus a0 respectively. The major axis is always the longest distance across the ellipse and can be horizontal or vertical. Thus, the length of the major axis in this ellipse is 2a. Furthermore, P and P, uh, is it P naught? How do you pronounce? Are called vertices of the ellipse. The point Q and Q naught are located at the end of the minor axis of the ellipse and have coordinates 0, b and 0 minus b respectively. The minor axis is perpendicular to the major axis. So what they end up deriving it is this. Equation of an ellipse in the standard form would be like this. With center h and k. The foci are located as h plus minus c and k. The c square is a square minus b square. The equations of the directrices are h plus minus a square over c. A hyperbola can also be defined in terms of distances. In the case of a hyperbola, there are two foci and two directrices. Hyperbolas also have two asymptotes. A hyperbola is a set of all points where the difference between their distances from two fixed points, the foci, is constant. Hyperbola is a set of all points where the difference between their distances from two fixed points, the foci, is constant. A typical hyperbola in which the difference of the distances from any point on the ellipse to the foci is constant. Then I'm getting confused. It says difference between their distances. The difference between the derivation of the equation of a hyperbola and standard form is virtually identical to that of an ellipse. One slight hitch lies in the definition. The difference between two numbers is always positive. Let P be a point on the hyperbola with coordinates x, y. Then the definition of a hyperbola gives distance from P to F1 minus distance from P to F2. Oh, I see. So distance from here to F2 minus here to F1. It will be a constant throughout the entire line. The equations of the asymptotes are given by y is equal to k plus minus a over b x minus h. The equation of a hyperbola in standard form. Consider the hyperbola with center hk, a horizontal major axis and a vertical minor axis. Then the equation of this ellipse is this. The foci are located at h plus minus c k, where c square is equal to a square plus b square. The equations of the asymptotes are given by y is equal to k plus minus b over a x minus h. If the major axis is vertical, then this is the equation. The eccentricity E of a conic section is defined by the distance from any point on a conic section to its focus, divided by perpendicular distance from that point to the nearest directrix. This value is constant for any conic section and can define conic section as well. If E is equal to 1, the conic is a parabola. If E is less than 1, it is an ellipse. If E is more than 1, it is a hyperbola. The eccentricity of a circle is 0. What's the directrix of an ellipse? I don't understand what it means by directrix of an ellipse. It's a line where the points are equidistant. But shouldn't that be a parabola? Recall from the definition of a parabola that the distance from any point on a parabola to the focus is equal to the distance from the same point to the directrix. So by definition, E is equal to 1. Therefore, by definition, the eccentricity of a parabola must be 1. The equations of the directrix of the horizontal ellipse are x plus minus a square over c. The right vertex of the ellipse is located at a0, and the right focus is c0. Therefore, the distance from the vertex to the focus is a minus c. And the distance from the vertex to the right directrix is a square over c minus a. This gives the eccentricity as c over a. But I don't get the definition of a directrix when it comes to ellipse and hyperbola. But how do you know? Like, okay, I would have to write proof for that the directrix exists at all. Like, there's a line. Uh, no, hold on. I need to understand the definition of a directrix. Polar equations of conic sections. So ellipse is this. Parabola is this. Hyperbola is this. General equations of degree 2. Graph of the equation of this form is a conic section. If p is not 0, then the coordinate axes are rotated. To identify the conic section, we use discriminant of the conic sections for AC minus p squared. One of the following cases must be true. For AC minus p squared is more than 0. If so, the graph is an ellipse. For AC minus p squared, then the is equal to 0, then it's a parabola. For AC minus p squared, the graph is a hyperbola. Yeah, I think I will study more upstream. Well, I gave myself a lot of homework. But stream wise, I think I'm done with calculus 2. I wouldn't say I'm like good at it, but at least I know the material. At least I'm familiar with everything now. Next stream, I don't know what I would do. Maybe something programming related. We will see. But yeah. So where has this been the entire stream? Yes, I will end the stream here. And either I would start a programming stream. Maybe I will take a break from streaming calculus. And I might stream something else. Okay, then I will end the stream here. And see you next time, I guess.